Get going with the last talk of the day. There's some real pressure on Marian here because he's the guy who keeps us between stops us getting to the bar. So this better be a really good talk.
Or I'll give you beer.
Or he'll give you beer. Okay, so everybody, welcome Marian.
Hello. So my name is Marian Marinov. I'm the Chief System Architect of SiteGround, and I'm also the head of the DevOps team at SiteGround. In my spare time, I teach network security courses and Linux system administration courses in Softuni and Sofia University, and I'm also organizer of OpenFest, Pro workshops, WCBG meetings, and stuff like this. So today I'm going to talk about data center networking for the cloud, and the disclaimer here starts with you have to think for the worst situation for the network, not for the best situation for the network. This is the base of this talk, okay? So let's start with some history. We had data centers with only physical machines, and on these physical machines we had only a few hundred IPs, and I'm saying only here, per machine. So one machine, a few hundred IPs. Then the virtual machines came, and now we have a few IPs on the virtual machine, but we have multiple virtual machines, like hundreds of virtual machines on a single node. So the density changes, and now the containers came, and you have actually thousands of containers on a single machine. That's not a problem to have thousands of containers on this one machine. This means thousands of IPs. And here I have some numbers that we have to remember. So if we have a 42 unit rack, we have 42 physical machines. With physical machines, maybe if we have 100 IPs per machine, we have 4,200 IPs for the rack. But if we have VMs on that rack, on the same that rack, with the same machines, we could actually have 42,000 IPs. And with containers with only 2 IPs per container, at average, you would get 84,000 IPs in a single rack. And that's a single rack, and you have data centers with a lot of racks. So try to remember these numbers. And the problems that we start with are first, broadcast storms. A lot of people think that switches nowadays handle these with broadcast storm protection and stuff like this. Switches that enable the broadcast storms protections, usually when this is you reach this limit, you actually stop half of your network. Instead of solving the problem, you're creating another problem. So the other thing is MAC and Arp tables that are limited on your switches. And the final thing is bandwidth. For the bandwidth, nowadays it's not a big issue, but we'll discuss it in detail. So we start with the broadcast domains. A lot of the protocols that we are currently using are using broadcasts or multicast. So ARP, IPv6, ICMP, DHCP, multicast DNS, and if you have high availability systems, they're the worst because they try to communicate at a very rapid pace, which means that within a single second you may send 10 or 100 packets just to make sure that 1 or 2 or 10 machines are currently working. All of them are working. So the other thing is if you have systems like Console that is using gossip type protocols, this means that you would get first broadcast storm from the UDP traffic of the Console, then you have broadcast storm from the ARP because all of these machines will ask for other machines' IPs. And this may actually bring down your network. And I'm saying that this is a certain thing because this happened to me in 3 data centers around the world when a network operator from the data center called us and said, "Did you actually deploy something today?" Yes. Can you stop it, please, because it broke the network? Yes, it actually broke the network. We had 50% packet loss within that network in each of the data centers. And we were gradually adding machines. At a certain point, we added only 20 machines to the console cluster, and the whole network collapsed. So I'm not telling you how many machines we had in that data centers, but there were not so many, less than 400, less than 200 actually, at certain points. So 42 machines are fine if they're the only 42 machines that you're going to work within the network. Now when you have 10 racks, you have 420. And in a data center, you have a lot more racks. So 4,200 machines, it's okay for a mid-size data center. And you have to have network for these machines. So in a typical data center, you get a switch that's the specs. And I'm not telling you it's a brand, this brand. The typical data center switch would have something like 1 terabit throughput or more. But let's say that this is in the middle, 1 terabit. And this is something that you would look for in the specs, right? Then you would look for the maximum packet rate per second, right? So 600, 700 million packets per second. That's okay for a medium-sized switch. And then you have this, 48 to 64K MAC address table. One rack could have 84,000 IPs easily. And if you have one VLAN there, that is the whole rack, now this is not working. Now you don't have network, because your switch is working on like 35 to 50% of its possible performance, because the MAC address table is constantly cleaned up. So yeah, 1,000 containers per machine. This is not so big number. I have seen people running even 2,000 or 4,000 containers, because each process is another container for them. They decided this, that's fine. Linux can handle maybe 100,000 processes per machine easily. So if each process is a container, yeah, what if we have teraracks? We have this very big problem that we have to solve now. The Linux Arp table is very small, actually. On a Linux host, the default is around 1,000 IPs that you would cache in the Arp. And strangely enough, it's not very easily changeable, because you have to understand the garbage collector thresholds for 1, 2, and 3, and you also need to know about the 2 times that you have for first threshold, for the second threshold, and for the third threshold. So in my presentation, I have a lot of links. I have already uploaded the presentation, so you can click on these links and get all the information you need. But the idea here is that you need first to change the defaults on your Linux host in order to be able to get more MAC addresses in your Arp table. And if you ask most of the system administrators, Linux system administrators, how would they do that? They would not remember this. They may have read about it, but this is something that almost nobody changes. So this is the first thing. You break the network and you now don't know how to fix it, because this is very rarely used. I'm sorry. Now, for the bandwidth, we have some assumptions here. Let's say that a physical machine averages at around 200 megabits per second. Let's say this is the average, and this is maybe not the worst. You could have average of 1 or 2 gigabits easily. But let's say that most machines, their workload is around 200 or 300 megabits per second. This is a physical machine. Then you split this workload into different virtual machines, but try to use more the virtual machines. So let's say we have 100 megabits per virtual machine. If we have 10 virtual machines, we would need 1 gigabit. But if we have 100 on this machine, we need now 10 gigabit uplink for this physical machine. This is one machine from the rack, 10 gigabit link. If we have a lot of containers and each of them is averaging 100 megabits, we need 100 gigabit interface on this machine just to push out the traffic to the network. Then, what about the switching of this thing? 42 machines with 200 megabits average, 8.4 gigabits. It's not bad, it's not a problem. Probably all switches should handle this. But 420 gigabits switching, you need a little bit, and you cannot go with the cheapest switches now. And when you go to the 100 gigabit links, there is no cheap switch for 100 gigabit. And you need 4 links from the machine to the switch just to push out the traffic from this one machine. I'm not saying that it's actually feasible to get 400 gigabits from one machine, but with a lot of tuning, it may be possible. So linking these switches usually is a problem, because now for each switch, the standard data center networking was FAT3, which means that one switch is 1 gigabit, and you get, for example, 2 or 4 gigabit uplinks from it. Each port is 1 gigabit, 2 or 4 gigabits trunked to the bigger switch. So now you have, for example, 48 port switch, 44 are for the clients, 4 for the uplinks. But this means that 44 gigabits are using only 4 gigabits uplink. This is oversubscription of the switch. Then on the aggregation switch, you aggregate multiple switches, and then you have, for example, for this switch, 40 gigabit uplinks, maybe 4 of those to one core switch that would connect all of your networking. As you can clearly see, this is oversubscribing all of your links. So when 1 or 2 switches start to use all of the bandwidth, the clients on these switches start to suffer. So trunking was the only way at that point. And 40 gigabit uplinks is not a standard in every data center. So a standard currently is around 10 gigabits to get multiple of 10 gigabits, but multiple of 40 gigabits from one switch to aggregation is not something that every data center would provide. Obviously, 100 gigabits is something that requires custom order that they wouldn't have at all in their data center. So getting out all of this traffic from your machines to the internet or to another machine inside the same data center is problematic. So we go to the solutions now. First, the separation of the networking. Nobody should be making one broadcast domain of, let's say, 1600 or 3200 machines. Nobody should, but there are office networks that actually do that. So in the data center, I have seen actually flat networks that aggregate thousands of ports in a single VLAN. That's a problem, obviously. So VLAN is the first solution to simply limit the broadcast domains. But you have only 4,000 VLANs. And in a data center, even with 1,000 racks, you may actually have 1,000 clients that may actually require more than 4 VLANs each. And you're out of VLANs. Then you go to Q&Q, and with Q&Q, you get a little bit more VLANs, but you're losing from the maximum transmission unit. So not everyone wants that. And then there's the Mpls that most data centers don't provide directly MPLS. You can get MPLS from the telecoms, but inside the data center, MPLS is a more exotic thing. So you cannot ask for that directly. The other problem is that not all switches support per VLAN MAC address table, which means that even though your switch has VLANs and your broadcast domain is smaller, you still have the VLAN table, the MAC address table that is only 64K, which is a problem. There are switches that support 64K per V1, which is nice, and at that point you are solving some of your problems with the MAC address tables, but you're not solving all of your problems. The rest is the capacity of these switches. As I said, trunking these uplinks is not enough, let's say. So the other problem is that your network now, if you have a lot of VLANs, QNQ, MPLS, it's not simple anymore. You need to configure it and make sure that it stays configured like this. When a switch breaks, you need to make sure that your provisioning system will provision the switch exactly with the same configuration as the previous one. Unfortunately, the networking equipment currently changes very fast. So if you bought a switch last year, it's possible that this year you cannot buy the same switch. It's strange, but you can buy the same switch on eBay a lot cheaper without support, but you cannot buy the same switch, the same model of the switch this year. It's possible. So these changes and these V1 configurations, they are not simple. All data centers are using some kind of management software. Some people wrote their own, some are using open source, others are buying network management software. And this software sometimes introduces other complexity problems, like I now cannot provision more than 100 VLANs per port because I have set some limit somewhere, and now this client cannot get his VLANs to this switch. This VLAN is prohibited from using on this type of switches, this VLAN is prohibited on that type of switches, and stuff like this. So VLANs and QNQ, not the simplest solution. So Cisco came out with layered topology design, and since 2008 there are a few little changes within the network topology. This is what I'm going to talk about. So you get 3 different types of networking. You have your access switches that are running, let's say, top of rack. And then you have aggregation switches, which may be end of line or end of a few lines. And then you have the core networking. Who here, everyone knows what CWOS is, right? CWOS. Okay, so the idea here is that in plain English, it's using equal cost multipath on your switches for distributing your traffic. The problem is that on Ethernet, we cannot actually use multiple links with equal cost multipath simply because we use spanning tree to prevent loops, right? Which is a problem. So this here stays within the spanning tree, spine and leaf topology, where you have a few access switches, top of rack switches, that use the normal fat tree topology, but they have backup links with other switches. With this in mind, Facebook then came out with DataCenter fabric design, which is similar, but instead of having Ethernet on after the aggregation, instead of keeping Ethernet here between the access and the aggregation switches, they actually removed it and moved to layer 3 for everything. So I'll try to explain it here because this picture here is a lot more complex. There is a link to the paper of Facebook if you want to read it here, and a little bit more humane explanation on their blog. So let's explain it like this. Your top-of-rack switches are aggregating, are collecting your ports from the servers. From there, you have only layer 3 IP directly to route the traffic. Using equal cost multipath, you can simply add more links for your, to your switch to increase the maximum capacity. So if you want to have 48 port gigabit switch working at its max, you would need 24 ports for downstream to the servers and 24 ports for upstream to the next layer. And you're using equal cost multipath to the other 24 uplinks. The ease of this is that you can start with 2 or 4 uplinks to the core networking, but to the fabric switches as they're called here. And when you need more capacity, you simply add more links to the fabrics. The fabrics are more complicated switches with hundreds of ports and a lot more capacity, but your top-of-rack switches are a lot simpler now. They only need to have BGP support and everything works. So the idea is that the fabrics are then again by layer 3 connected to the spine plane, and the spine provides connectivity to the outside world. Everything that stays within the network actually stays between routes, and this is routing here, between the fabric switches and the spine switches. That's it. So when this is working normally, you would have equal bisectional bandwidth across all of your data center. Bisectional bandwidth, somebody that doesn't understand this? Okay, so the idea is that within a data center, you cross a line between two points in the data center, and you should have the maximum link capacity between one side of the line and the other side of the line. So this is how you design the networking inside your data center to get the bisectional bandwidth across your network. Google decided to do almost the same thing, but they wanted to remove the programmatic problem here, because what happened is with the previous, here you need to configure a lot of things in BGP, and we all know that things happen with BGP sometimes, and network breaks. And when BGP is running your core network, breaking it means breaking your whole data center. So Google wanted to remove a lot of that, and they decided to make their own networking. So they built their own switches, their own line cards, the whole motherboard and everything, and build it in a way that they don't need to reconfigure everything every time. They simply get a line card into a chassis, and you get the base configuration for this one card. So all VLANs and all the BGP you need. You have a supervisor process that is connected to one central place, one single place. Instead of having multiple BGPs configured across all of your network, you have one single place that is configuring all of your line cards, and your network now stays the same even if you move one line card from one chassis to another. Again, the paper here, you can read it. And so the solution in most places is something that would reduce the amount of broadcast and would reduce the amount of ARP and MAC addresses that you have within your VLAN. The problem with VLANs is usually that they are easy within the data center, but they are very hard between two data centers and almost impossible between two continents. So when you want to have a private network between two continents, that's a problem. So VX1 and NVGRI are trying to solve this problem. If we have a few containers on one machine and a few containers on the other machine, and these machines are connected with a single Ethernet interface to the switch, we create a virtual pipe between those two machines. And we route the traffic from one machine to another machine, routed via tunnel. And we have either VX1 tunnel or NVGRI tunnel. So the idea here is that we have routing inside the host node. So this part here is one single host node, and this part here is another single host node. You route the traffic across this tunnel, and what you get inside the network on the switch, you get a simple unicast packet from this host to this host. If you have hundreds of containers on one machine and hundreds of containers on the other machine, and they're talking, and here I'm saying things like APIs, get this picture from there, put this thing in the database, is this user logged in, and stuff like this, you know, the fan-out architecture for the websites. So instead of having multiple ARP packets and multiple IP packets with different sources and destinations, you now have single MAC from one machine to a single MAC from the other machine. So you aggregate this, but you have to know the routing across your network, which is a problem because VX1 can be point-to-point or multicast, but it is configured usually either with IP route 2 or with Open vSwitch. If you're configuring it with IP route 2, this means that somebody has to create these routes and these VX1 interfaces and these routes, and then somebody has to configure them on the other machine and has to keep them in sync as a configuration. Something that we historically did with BGP for the networking, now we have to do with shell scripts and other tools. Open vSwitch can configure these dynamically, which is very nice because you configure the network on one place, and everything that is connected to the Open vSwitch network now knows which VX1 interfaces has to end up on this machine. And for the VX1, the problem is you have 50 bytes overhead. So you either have hardware support for these 50 bytes, or you increase to jumbo frames. And with jumbo frames, you have these other problems like tools like SSH that for each kpress they send a packet. You lose a lot of, you send a lot of packets almost empty. Arista and Brocade actually have hardware support inside their switches for VX1, but this is not Open vSwitch, it's simply VX1. You can terminate VX1 directly into the switch. NVGRI is similar to VX1, but the idea there is to create grid tunnels and route the traffic over them. The problem with this is that it's only supported by Microsoft, as far as I know. But it works on Azure, so I have read a few articles about this. The overhead there is only 42 bytes. The other solutions are things like Genevi. Genevi, the idea there is to have the same thing like VX1 and NVGRI, but to be unified. So Genevi should support VX1 header, NVGRI header, and also stateless transport tunneling headers. It's supported by Open vSwitch. I don't know if it works dynamically as the VX1 support of of Open vSwitch works, but there are tutorials how to set up this. Cisco made a very nice comparison of these overlay technologies. So here's a paper that you should read to see this. The ideas of all of these overlay technologies is that you would reduce the amount of MAC addresses within your network when you're talking between your servers, and you would reduce the complexity of the VLANs by moving those things from the switches to the end servers. Hopefully, you would have better control on the end servers instead of the switches. So my conclusion here is you should use layer 2 only for the first cable, and that's it. After that, you need routing. That's it. After that, you cannot use Ethernet for so much port and so much bandwidth. Overlays can help with specific setups where a client wants his one rack in Chicago to connect to one rack in St. Louis. It's pretty easy to simply sync those, connect them with some overlay, and you would have this okay, not simple, but easier network to handle for the client. The client would have his own virtual private network over the internet. And now questions. Yeah.
What about layer 3 to the host?
Layer 3 to the host, it's possible. The problem with this is if you don't run the host, it's problematic for setting up on the host. It's very nice, and when you can do it, it's even better idea, because you would limit the layer 2 only to the host itself. The problem there is that most applications, they want layer 2. They want their router. They don't know how to configure routing. So provisioning these applications with layer 3 directly is sometimes problematic. On the other hand, the other problem with layer 3 is if you're using layer 3 only on IPv4, you don't have enough IPv4. So even if you're using private interfaces, private prefixes, you still don't have enough of those. With the huge number of IPs that you are required to have on a big scale, you simply don't have enough of those. Other questions? Anyone using VX1 or NVGRI?
Have been using it previously or KVM or CloudStack?
Yeah, it's pretty nice to connect like 100 machines here, 100 machines there, and it works, and your switches don't break.
Mpls?
Mpls, yes.
Mpls is the classic for that. That's the canonical way of doing it.
When you're an ISP on telecom, yes, but in the data center, have you seen it?
Stuff I've seen at customers, VXLAN termination on the top of our switch is a lot more common than getting VXLAN to the host, for whatever reason. VXLAN using EVPN signaling is quite common, but VXLAN with multicast signaling is also as common as VXLAN with EVPN.
The problem with the multicast is that at certain data centers, I'm not saying the names, multicast is actually forbidden.
Yes. So you mentioned VXLAN termination is supported by Brocade and Arista.
Yes.
I've seen it being used with other vendors. Cumulus Linux is quite common for
I like
top
those
of rack
guys.
switches at least, right?
Yeah.
Other than that, yeah.
MikroTik also supports that.
Cool.
I'm not putting that in the data center, but yeah, they support it.
And one more point. So you showed kind of this leaf and spine work
Yes.
with 3 tiers.
Yes.
I wanted to assure everyone that it doesn't need to be that complex.
Yeah.
So if you only need 1,000, 2,000 ports, you can do it with 2 tiers, and that's perfectly fine and a lot simpler than doing a 3-tier leaf and spine.
Actually, when I was reading
Huge
for
Facebook thing. Right?
for not the huge thing. This is only in Facebook, but
Yeah.
when I was reading for this
Oh,
leaf
no.
and spine networking here from Cisco, they were doing this only 2 tiers. And when I saw them in a paper, they wrote that the core was actually not Ethernet but InfiniBand instead of Ethernet directly.
So the diagram on the next page, I've seen it at quite a few customers. No,
Yeah.
not this one. The
Yeah.
Facebook 2-tier one.
Yeah.
Yeah, this one.
Uh,
No, not this one.
Okay. Give me a sec.
Okay.
This one.
So this kind of topology, quite a few people use this kind of topology, and it's usually smaller. It's usually like 10 top of rack switches and 4 spines, right, or something like
Yeah.
that. And this scales easily to 1,000, 2,000 ports. So if you only have 1 or 2,000 servers, you can put them on a network like this, and it's very cheap, right?
My only question that I had when I saw this for the first time was, how are they routing this out of the network? Because inside the network, it's fine. So when I asked a few Facebook guys, they actually told me that they have routers that they dedicate some prefixes only. So if you have 10 gigabit links on the spine here, they also have 10 gigabit links to routers, but not to a single router, to 4 or 5 different routers.
Where routing to the outside world lives in this topology is not on top of the spines, it's obviously down there. So like a router to the outside world would be number 1 or number 2 in the topology.
It looks like a top of rack
Yeah,
switch.
yeah.
Yeah, the same connectivity. Anyone else? Questions? Thank you.